For the past 2 days, we've been doing activities that have been exploring some of the basic properties of positive and negative numbers. You've used thermometers, which are essentially number lines, and then you also learned the idea that when I add a negative to a positive 5 and then a negative 5, any number added to its opposite always equals 0. At this point, we're going to move forward with a more formal study of operating with integers, but first we need to define them. When you first learned about numbers when you were little and you were watching Sesame Street, you learned 1, 2, 3, 4, 5, 6. In fact, all of mankind's first experiences with mathematics were about counting. So if I were to represent that on a number line, I could draw. This time it's going to be horizontal. If I draw a number line, and I have 1 right here, and then 2 right here, and then 3 right here, I will have the counting or natural numbers. Whoops, natural. URAL numbers. And if I was to talk about set notation, it would start here, go 1, 2, 3, and then it would say dot, 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 which means forever or infinity in mathematics. Then, in several parts of the world, different people came up with the concept of 0, including the Mayans in Central America and the Indians and the Arabs, and so they added that to the number line. And this set of numbers is only different from the counting numbers in that it has 0. And one way you can remember that is it has an O, and the O is like 0. The whole numbers looks just like that in set notation, except it starts with 0. And it goes on. Oops, I skipped 2. It goes on forever as well. Notice that the whole numbers are these numbers that are right on the notch. They're not the numbers in between. Whole. They're the whole thing. If I were thinking about pizzas, the whole pizza, 2 whole pizzas, 3 whole pizzas. That's what makes them whole numbers. The numbers in between there, like the fractions and the decimals, are actually called rational numbers, because they can be expressed as a ratio. We're going to take that up later in the year. As a ratio. That's where you hear that rational numbers, ratio. That leaves us now to the idea of integers. Integers came into the picture when people wanted to talk about debt, when you owed money, when you have less than 0. There was not a number to define that. So we had to get into the negatives. And as you can see from the number line, and I think you already know this, that negative numbers are less than 0. The negative integers are like the whole numbers. They're the things that are right on the notch. They're not the numbers in between. So all negative numbers are not integers. The integers are special negative numbers that are exactly right on the notch. And that leads us to the definition of integers are whole numbers. Remember what they are: 0, 1, 2, 3. Whole numbers and their opposites. So note, not all negative numbers are integers, just whole numbers and their opposites. So, is negative 2 an integer? Yes, because it's the opposite of positive 2. Is 4 an integer? Yes, because it is a whole number. Is 1.5 an integer? No, because it's not a whole number. It's a part. It's like 1.5 pizzas. okay, and negative 1.5, it also is no, because it's not whole. So now that we've got the idea of what an integer is, we're going to start thinking about how we operate with them. Every time you've learned a new set of numbers, you've learned how to then add, subtract, multiply, and divide. And so today we're going to talk about adding integers, and we're going to begin with simulating the experience of the activity that you did in class before this. So hopefully you've got your thoughts all geared up toward this notion of using checkers to represent positive and negative numbers. So if I have a black checker, it's going to represent a positive number. And if I have a red checker, it's going to represent a negative. So the beginning of this is really simple. I have 3 black checkers to begin with, and I put in 2 more black checkers. Clearly, you all know how to count, and that means that I have 5 black checkers. If I were to represent this using mathematics, or just the abstract numerical expression, I would say that positive 3 plus positive 2 is equal to 5, something you already know. And you also know that if there is no sign, it means that it is positive. All right, so we can see that a positive 5 plus a positive 2, positive 3 plus positive 2 is equal to positive 5. By the same token, if I have 3 negatives and I add 2 more negatives, or 3 reds, and I add 2 more reds, I've got 5 reds. So in this, I can see, if I were to represent that with numbers, negative 3 plus negative 2 equals negative 5. I really want you to think about this common sense representation, this modeling, because right now, learning one operation at a time is really simple. But for some kids, these ideas start to swim in their mind when they try to memorize. So rather than memorize, look at this right now, take it in. If I've got all positives and I'm adding together, they equal a total, oops, I should have gone back to black, and then this gives me a total of 5s. So anytime the signs, and what's the same about these, that the signs are alike. Oh, geez, I can't seem to spell. S-I-G-N-S, are alike. So the answer has all of the same in the end. What we did was added. Let's take a look at what it looks like if I put some positives together and some negatives. And I want you to imagine it's a battle. Say I have, I don't know, how many fit? 1, 2, 3, 4, 5. Let's say I have 6 blacks, and they are battling 2 reds. Okay, I can see that these guys can take each other out. These guys can take each other out, and the blacks win because they have 4 more. What this is showing in numbers is if I have positive 6 and I add, and in most of the papers that you have, they'll put this in parentheses, but don't be confused, because remember what we said? It's not grouping symbols unless there's some, in order for it to be grouping symbols, there's got to be something going on inside. This is just to set off the negative. So notice here we have unlike signs. I've got a positive added to a negative, and what I ended up with was positive 4. Think about that for a minute. Let's do another one. Let's say, if I say 3 negatives battle 1 positive, so I've got negative 3 plus positive 1 these guys take each other out, and it equals, remember the reds are representing negative, -2. Let's study these two examples. 6 plus -2 is 4. -3 plus 1 is -2. Notice that these get taken out. The answer is the difference between the positive and the negative. Difference, as you'll remember, really infers subtraction. So the way that a short way of doing this without getting checkers out is 6 minus 2 is 4. And the reason I know it's positive 4 is because this side in the battle had more to begin with. All right, in this example, -3 plus 1, 3 minus 1 is 2, and I know that it's negative because the negatives had more to begin with. What we have discovered. We've discovered when we have like signs, in other words, they're all the same, we simply add. And if they're all negative, the sign is negative, okay? With unlike signs, we subtract. In either situation, we're going to use the sign of what we might call, using the checker notice model, is the sign of the team that had more, the sign of the winner. For now, before we learn what absolute value is, we're going to call it use the sign of the winner. And you can see when they're like signs, everybody, they're all the same. You have to use the sign that they all are alike. Like I said, I really want you to get in the habit of thinking about this. In the beginning, I want you to think using checkers. But as you get examples, you might say -11 plus -5. The first thing you want to ask yourself, these like signs or unlike signs? Clearly they are like signs, which means we're adding. 11 plus 5 is 16. And we are using the sign of the greater, right? We're using that sign. Because if I have I've got 11 negative checkers, red ones, and I put in 5 more red ones, I've got 16 reds, which means 16 negatives. So we're still going to use the sign of the winner. The winner is 11. It's the bigger, what we call absolute value, but we'll get there later. If I say -11 plus 5, I can see that these are unlike signs, which means I know I need to subtract. 11 minus 5 is 6, and again, 11 is the winner, so the answer is -6. The important thing when you first start doing this is to go slow enough so that you can look and you can see what you're doing, and make sure you're following these rules. Like signs add, unlike signs subtract, always use the sign of the winner.